Okay. Is there anything else I'm supposed to be doing? It's been so long since I had a class like this. Okay. Okay, so we are actually sort of more or less a little, like temporally a little less than halfway through the course, but sort of conceptually more or less halfway through the course. So we've done divide and conquer and greedy, and then the two bits that I think that, that really sort of teach you the paradigms of algorithm design are dynamic programming and NP completeness. And then there's a load of stuff at the end that's mostly graph algorithms, but it's sort of a mixed bag. It's like bridges and flows, flows, and paths, a lot of stuff about shortest paths, all pairs, shortest paths, when you have negative weight edges, when you don't have negative weight edges, blah, 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 blah. So that's sort of going to be like the fifth thing, which I stuff in there, all of the things that the other professors insist I have to teach you, and I can't really sort of figure out you have to know these algorithms, but I can't figure out exactly what ties them all together. So that's the fifth thing. So before the second midterm, we're going to try to get through dynamic programming and NP completeness, or at least the parts of NP completeness that the faculty insists that you know, and then we're going to do the fun parts, which nobody normally teaches in undergrad, but you're lucky and you're going to see. First, I'm going to introduce you to dynamic programming. Now, normally people do like knapsack, but I'm going to do the same sort of thing with Huffman, so that we did with Huffman, which is sort of introduce you to a really hard, serious problem, which is called edit distance. So I do bioinformatics, sort of, sometimes. I do data structures for bioinformatics, and one of the key things in bioinformatics is aligning DNA sequences. And the best currently we know how to do is quadratic time, and there are actually lower. Now, we don't actually do it in quadratic time. We use much better than quadratic time because you never want. Oh, okay, we'll get to that. But as a warm-up, we are going to play a game. We are going to play the matrix path game. Okay, so this is like snakes and ladders, but maybe not as fun. And also going in the opposite direction. Okay, so the rules of this game are you start at the top left. Okay, you start here. Can you see the green? Well, you can at least see that it's green, right? And it says, believe me that it says start here. Okay, so the rules of the game are you start here, and you have to end here. Okay? And at each step, you can go right or down, or diagonally right and down. Okay? So one cell. Okay? You start here, and at each step, you can move one. Okay? Now, I believe that it is in fact green. Okay. It also says start here. Okay, so the rule is if you go right or down, the only arrows going right and down are black. Okay? And you pay $1. Conceptually, not really. I mean, this is how I could like make a lot of money out of this class, but we're not actually going to do this. $1, a unit of whatever, a time unit, whatever. Okay. So at each step you can move one cell right, one cell down, or one cell diagonally right and down. Following a black arrow costs $1, but following a red arrow is free. Okay? You must reach the bottom right corner. What is, and at first what is the cheapest path through the matrix, but then actually I only really care about what is, to begin with I only care about what is the cost of the cheapest path. Okay? So, does everybody understand the rules of the game? Yes. Okay. At least one person. Okay, that's good. And that was to all attendees. No, that was to all panelists. No, black arrow costs 1, red arrow is free. Okay? Okay, otherwise it would be pretty, yeah, because otherwise you would just be like, if black arrow is free, you just go zoop, zoop. Because down is always black and right is always black. The red arrows are only diagonal and only on some of the diagonals. Yeah, it's not exactly random. You can think of it as random for the moment. Yeah, sure. You can think of it as random. Okay, so now I was going to start this class. I think I taught this. So I was going to tell you about when I was in high school. We had my biology teacher, Mr. Klages. And he was very, very laid back. And there was this student, Ryan, in my class. And Ryan would realize that if he just asked Mr. Klages, and he did this all the time, he wasn't actually that stupid, but he would do this for fun. He would say, Mr. Klages, I don't know what the answer to number 1 is. And Mr. Klages would say, oh, well, how would you figure this out? If you could figure out this and this and this, then you could figure out the answer, right? And Ryan would say, yeah, but I don't know this and this and this. And Mr. Klages would say, oh, okay. Well, to figure out this, you would figure out, if you knew this and this and this, then you could figure out this. And Ryan would say, yeah, but I don't know those either. And then he would go on, and finally Mr. Klages says, well, you could figure out this, and then this would be this, and this would be this, and this would be this, and then that would be the answer, wouldn't it? And Ryan would say, oh, yes, thank you, and would write down, Mr. Klages, I don't understand question 2. And I don't know how he got the patience. It took him way longer to finish the test doing it this way than if he'd actually just memorized the answers. But in honor of Mr. Klages and Ryan, we're going to think about figuring out the cost of the cheapest path through this matrix the way Ryan would. Okay. Now, what we're going to do, one of these 2 blue markers is actually going to work, but one of them doesn't. Yeah, that seems to be maybe the one who works. Now, you want the cost of reaching this, so this cell, okay, the cost of reaching, you start here, the cost of getting to that cell is 0. Do we try to find the largest bit strings of red arrows? Not necessarily, because, for example, it could be that you have a longer, well, sort of. But no, not necessarily. Because it might be that you have slightly fewer red arrows if you go some other way, but the path is actually shorter. So you manage to, you don't have as many red arrows, but your path is actually slightly cheaper. Okay? So you're just trying to minimize the cost. Yeah, I mean, obviously, if you can get lots of red arrows, that's good, provided that you're not going out of your way to get them. Okay. Later on, we'll have another problem that's more about crossing red arrows. Okay. So the cost here is 0. Okay. Now, can you see that 0, or should I make it in black? Can anybody see it? I can see it. Okay. I'll make it in black. Okay. That should be more visible. Can you see that 0? Okay. So notice that it's easy to figure out what the top row is, right? Because I told you that the reds are only ever diagonal. So if you want to go here, the only way you can go from here to here is by crossing two black arrows. So this is, the cost here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you know the cost, the minimum cost of getting to any of those squares. Same thing down here, minimum cost is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What about the cost of the other things? Well, what's the minimum cost of getting here? Who knows? But now we want to figure out the minimum cost of getting here. Now, if you were Ryan, and you would ask, let's pretend I'm Mr. Klages. You would say, what's the cost here? And Mr. Klages would say, oh, well, if I told you this is an X, this is a Y, and this is a Z, can you see these? X, Y, and Z? Yes, good, okay. If I told you what X, Y, and Z were, which I actually haven't worked out, could you figure out what the cost of this is? Right? Could you figure out the cost, if you know the minimum cost of getting to Y, the minimum cost of getting to X, minimum cost of getting to Y, and the minimum cost of getting to Z, could you figure out the minimum cost of getting to the bottom right corner? Yes, I'm going to take that yes as a yes, you could figure it out. Okay, what would it be? Close. It would be min x plus 1, y plus 1, z plus 1. And the reason I'm not writing min x, y, z plus 1 outside the brackets is, you'll see it in an Excel. The cost is 6. Let's not get ahead of ourselves. I don't know if the cost is 6. Maybe, but we actually don't care about the actual cost. We just want to learn dynamic programming. So we're going to learn dynamic programming with this, and then okay. So now, that was the first where Ryan asked, Mr. Klages, I don't know what the cheapest way to get here is. And Mr. Klages says, oh, well, how would you work this out? You would take like X and Y and Z, and then if you knew those, you could work this out. And Ryan would say, but Mr. Klages, I don't know X, Y, and Z. Yes. Oh, so the plus 1 is because if you were at X, you would still have to move here. So if you know the cost of Z, then the cost to go here is the cost to get to this one plus 1. So maybe it's cheapest to get here and go here, but that's still 1 more than Y. Okay, so if we're writing in the cells the minimum cost of getting to those cells, we've got the top row, the leftmost column, and we're saying if we knew X, Y, and Z, we could work this one out. I'll put a question mark here, okay, because that's what we actually want. And then, so Ryan would ask, but Mr. Klages, I don't know X, Y, and Z. And Mr. Klages would say, well, in that case, if I told you S, T, U, V, W, then could you work out X, Y, and Z? And Ryan would look at it and say, maybe, because, for example, if I tell you S, T, U, V, W, could you work out X? What is X? Well, X is like the same thing, right? So question mark equals min of this. X equals min of S plus 1, T plus 1, and V plus 1. Okay, and Y is min of T plus 1 and U plus 1 and x plus 1. Now, Ryan doesn't know x, but he can work it out from STUV. So actually, if Mr. Kligas doesn't give him x, y, and z, he gives him STUVW, then Ryan can first work out x from ST and V, and then he can work out y from TU and x. Now here's where I didn't write the plus 1 outside, because what is z? Z is min of V and x plus 1 and w plus 1. Why is it only V? Because this is a red arrow. So if you can get to V if you can get here with cost V, then you can get here with the same cost. You can just go across the red arrow. Okay, let's catch up with what. Do you know that the arrows are all black in advance? What is the red edge pointing to x? Red edge? There isn't a red edge pointing to x. Okay, if there were a red edge pointing to x, then the red edges are always diagonal. If this were red from s to x, then I wouldn't put this plus 1 in. I would just say min of s, t plus 1, b plus 1. Okay, and so now the key thing is, well, okay, let's go back a little bit more, but not writing on the board because I'm running out of space. So then what would Ryan say? Ryan would say, oh, but I don't know STUVW. And Mr. Kligas would say, well, if I gave you these ones, could you work out STUVW? And then from STUVW you can work out XYZ, and from XYZ you can work out this one. And now the key thing is, to work out x, you need to work out t. And to work out y, you need t. But if you do this recursively, that's going to explode, right? I mean, if you just write this little recursive program that says, well, to figure out this, you call the program on x, y, and z calls it on v, x, and w, and x calls it on v, s, and t, you're calling the same thing on v twice. And then as you go up further in the matrix, the number of calls is going to explode. We're adding a cost to each edge and to each vertex here, or are the letters just represented? The letters are representing the cost, right? So here, I'm writing in the actual cost to get to this cell, right? The minimum, okay, what's the minimum cost to get to this cell? It's, what is it? Quick, can people see? What is the minimum cost to get to this cell? 1, yes, because there are several ways to get to this cell. I could go here and down, but that would cost me 2. I could go here and right, but that would cost me 2, or I can go straight. Now, what's the minimum cost to get to this cell? To get to this one. Also 1. Why? Because if I go like this and across, it would be 2, but if I go right and then diagonally, it's only 1. So this, the only way I can do it is 2, and then this, it's a 3, this is a 4. Why? Because either I can go here, down, one, and then across, or I can go straight across and then diagonally down. Red was double the cost. No, red is free. Red is free. Black is 1, red is free. Okay. So, we can sort of work these things out, right? Because if you look here, it's the min, since this arrow is black, it's the min of this plus 1, and this plus 1. So this is a 5. Okay, so for example, what is this? This is a 1. What is, so, okay, so in general, what rule do we have? In general, so we agree that this is sort of how we'd figure out this, and then if we had STUVW, we could figure out X, Y, Z. Just going to check the time, because I don't want the thing to stop recording. 5 minutes. Okay, so in general, if we call this whole matrix A, what we're going to say is, generalizing this, is that Aij equals min of ai minus 1, j minus 1, plus, I need a variable. I need an indicator variable. But I don't want to call it x. So I'm going to call it b, because, okay, it's either going to be 0 or 1. So it's plus b, or it's a I minus 1 j plus 1, or it's a I j minus 1 plus 1. Okay. Where b is 0 if the edge from, yeah, we still need the rules even though nobody can see them apparently. Okay, I'm going to write the definition of b down here. Okay, so b is 0 if the arrow from a I minus 1 j minus 1 to aij is red, and b equals 0 and b equals 1 if it's black. Okay? Are people okay? So people can see that if you have this recurrence, then if I told you x, y, and z, you could figure this out. And if I told you STUVW, you could figure out x, y, and z, and then you could figure this out. And in fact, if I tell you just that the starting cost is 0, you can figure out, well, you can't really apply the recurrence to the top row, but filling in the top row is really easy because there are no diagonal red arrows leading into the top row. So the top row is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can't apply it to the leftmost column because the leftmost column doesn't have anything, you can't, like, j minus 1 is not defined. But still, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so once you have those, if I ask you, well, what's the minimum cost to get to here, you can fill it in based on looking at the cost of this, this, and this. The cells above and to the left, and to the left. Right? So how would we do this? Could you write me a little program that computes the minimum cost of getting to the bottom right cell? Except if you do it recursively, you're going to call z. You're going to say, oh, to figure out this, I'm going to call z. I'm going to call my program on z, and then my program on z is going to call the program on x, on v, x, and w. And the program on w is also going to call it on v. So it's going to sort of explode because each cell is going to call it on the three neighbors, but there's a lot of overlap. So if you do it recursively, naively, you're going to get something that's exponential time. Just a second. But yes, conceptually it's very similar to